Greetings, my name is Russell Spencer, and this is an attempt at recreating my 2018 APS March Meeting presentation. There's a link in the description to the March Meeting page about the talk, as well as a link to the relevant paper. The talk is entitled Fluctuation Effects in A plus B plus AB Ternary Polymer Blends, and this work was done in collaboration with Mark Matson. This work examines symmetric ternary polymer blends consisting of A and B homopolymers as well as AB diblock copolymers. The important parameters in this model are the lengths of the polymers, NH and NC, as well as the copolymer concentration, 5RC, and the Flory-Huggins interaction parameter, chi-NH, which gives the strength of the A and B interaction. The fluctuations in this model are controlled by the invariant polymerization index, n bar. N bar is proportional to the length of the polymers and gives a measure of how well polymers can sample their environment. As the invariant polymerization index goes to infinity, the polymers can sample the environment perfectly and you obtain mean field theory. As the invariant polymerization index gets small, then fluctuations become more important. This ternary blend system has garnered interest because of its tendency to form this fluctuation-induced structure shown here, bicontinuous microemulsions. In this particular example, the system is about 10% copolymer, and the homopolymers are about a fifth the length of the copolymers. The invariant polymerization index in the system is quite large, being about 5,000 for the homopolymers. This indicates that bicontinuous microemulsions appear even when fluctuation effects are quite small. The parameters that we've chosen for our simulations are quite close to those used in experiments. The ratio of homopolymer to copolymer lengths is about a fifth, and we've chosen an invariant polymerization index of 10 to the 4. Let's start simple with mean field theory. So here I've shown the mean field phase diagram in terms of the amount of copolymer, phi c, on the horizontal axis, and chi n on the vertical axis. And you'll notice that I've flipped the vertical axis so that the high temperature phases are on the top. If there's no copolymer present, so phi c equals 0, homopolymers phase separate at a critical point at chi n equals 2. As you add copolymer to the system, the segregation is suppressed, and the critical point moves to higher chi n along what's called the Scott line. The Scott line terminates at a Lifshitz tricritical point, after which, when the system phase separates, it microphase separates into the lamellar phase. You might have noticed that bicontinuous microemulsions are conspicuously absent from this mean field phase diagram. When experiments are conducted, they see them between the regions of micro and macrophase separation, that is, where we see the Lifshitz tricritical point. When experiments are conducted, it seems like the disordered phase invades the phase segregated region, creating a channel of microemulsions that separate the macro and microphase segregated regions. In order to understand why this occurs, we turn to simulations. Simulations can be thought of as looking at fluctuation corrections to mean field theory. Here we compare the phase diagram found from previous simulations, denoted by the solid lines, to the mean field phase diagram seen earlier, denoted by dotted lines. When fluctuations are present, which is to say in the simulations, the transition moves down to higher chi n, and a channel of microemulsions opens up. This reflects what's seen in experiments. Although the simulations shown here were a leap forward, and they qualitatively capture what's seen in experiments, this is by no means the end of the story. They were done all the way back in 2004 when computational resources were not as available as they are today. They were also done in 2 dimensions. Dimensionality is an important consideration in critical behavior, so the critical point that they located may not be accurate. Bicontinuous microemulsions are also an inherently 3-dimensional structure, so can't adequately be captured in 2 dimensions. In our work, we do 3-dimensional simulations using finite size scaling to precisely locate the critical point. We then go on to examine the nature of the order-disorder transition by moving to higher chi n. But before I get to the results, I want to give you a brief primer on field-theoretic simulations. The usual way of simulating polymers involves representing individual molecules. One way of doing this is by employing the Gaussian chain model. In the Gaussian chain model, the internal energy of the polymer system is given by a combination of the A and B interaction energies, here shown as U, as well as the stretching energy of individual polymers. You can then calculate the partition function by integrating over all possible polymer configurations, scaled by this internal energy. Of course, this integral turns out to be extremely difficult, but it's a bit easier to deal with if we convert it from a particle-based representation to a field-based representation. We can perform an exact mathematical transformation of this partition function by inserting expressions involving 2 fields, here shown as W- and W+. W- is a composition field and it couples to the difference in A and B monomer concentrations, while W+ is a pressure field and it couples to the total concentration. We're left with a partition function that's given by a functional integral over these fields. Here the effective Hamiltonian H is given by a Hamiltonian for the non-interacting chains, as well as an integral over the fields themselves. If we want to do simulations or calculations in different ensembles, this is just a matter of swapping out the Hamiltonian for the non-interacting chains, here shown as HQ, for different functions. The Hamiltonian for the non-interacting chains is calculated in terms of the partition functions for the individual non-interacting chains, Q. The first term corresponds to the A homopolymers, the second term to the B homopolymers, and the third term to the copolymers. The partition function for the non-interacting chain, Q, can be calculated from the fields W- and W+. When employing the grand canonical ensemble, rather than writing the Hamiltonian for the non-interacting chains in terms of polymer concentrations, we write it in terms of fugacity Z, or chemical potential mu, which here gives the difference in chemical potential between the copolymers and the homopolymers. We also use a semi-grand canonical ensemble, where we fix the number of copolymers and we fix the total number of homopolymers, but we allow A and B homopolymers to exchange. The semi-grand canonical ensemble is useful for locating the Scott line, and the grand canonical ensemble turns out to be useful for probing polymer behavior and the nature of the transition at higher chi-n. In order to locate the Scott line, we consider this order parameter delta phi hat, which gives the difference in the average instantaneous A and B monomer concentrations. We then calculate the cumulant U in terms of the order parameter. We do this for different system sizes labeled L. This cumulant has three fixed points. Way above the transition, very large chi-n, where the polymers are strongly segregated, it tends towards 2/3. Way below the transition, where the polymers are well mixed, it tends towards 0. In between these two limits, there's a third fixed point, right at the critical point. By conducting the simulations in different system sizes, we can see where all of the lines overlap, and thereby locate the critical point. This first set of data was shown with no copolymer present. However, we can repeat this calculation with copolymer present and thereby locate the Scott line. The results of these calculations are shown here in this partial phase diagram, illustrated in terms of the amount of copolymer phi c, as well as chi-n. The points correspond to the simulation data, while the line corresponds to mean field theory. You'll notice that the Scott line terminates at this x, which is the Lifshitz point that I mentioned earlier. The Scott line calculated from simulations also has to terminate somewhere as well, so in order to probe what happens after it does, we'll move to chi-n equals 2.4 and conduct grand canonical ensemble simulations. We conduct these simulations at a given chemical potential mu, and we calculate the average copolymer concentration. Starting from a low mu, we gradually increase the chemical potential, which also increases the copolymer concentration. Eventually, there's a sharp jump in the concentration, which suggests that there's a first-order phase transition here. Starting from a high mu, we can slowly decrease the chemical potential, which also decreases the copolymer concentration. Once again, we see a sharp change in the concentration. This hysteresis loop is further evidence of a phase transition, and furthermore, it allows us to bracket the location of this transition. Taking a look at the A and B monomer concentrations, we can see that the lower branch looks like it corresponds to an A-rich or B-rich configuration, while the upper branch looks disordered but modulated, consistent with microemulsions. Moving on to a higher chi-n, we see very similar results. However, the distance between the upper and lower branches is much larger. This indicates a stronger first-order phase transition. Combining all the data we've shown you so far, we can create a still partial but more complete phase diagram. This phase diagram includes a two-phase region to the left, bicontinuous microemulsions to the right, and three-phase coexistence between A-rich, B-rich, and microemulsions in between. The large error bars in the three-phase region are because of the large amount of hysteresis that you saw in the last two slides. To summarize, we studied the compatibilization of immiscible A and B homopolymers by AB diblock copolymers using 3D Monte Carlo field-theoretic simulations. We started by focusing on finding the Scott line and assessing the importance of fluctuations near the transition. Moving to higher chi-n, we found a region of three-phase coexistence in Monte Carlo field-theoretic simulations. Unlike mean field theory, however, the A and B rich phases don't coexist with lamellae, instead they coexist with bicontinuous microemulsions. This brings me to the end of the APS talk. However, it should be noted that we've continued to work on the problem, and with the help of more advanced computational techniques, we've made significant advances. If you find this problem interesting, keep your eye out for an upcoming paper on the topic. Thanks for listening.